You probably know these sparklers from New Year's or birthday celebrations. What many people don't know is that they burn at over 1000 degrees Celsius, which is 2000 degrees Fahrenheit. But when you're hit by one of those sparks, it just tickles a bit, or at worst it stings a little. At uni we had a lab experiment in plasma physics. So me and my lab partner entered the room, and it had a plasma containment tank that looked a bit like the Trinity bomb. And I don't say that just to sound drastic or anything, it just had a similar size and look. The present postdoc cheerfully informed us that the plasma inside the container had a temperature of over 20,000 degrees, and at that number it doesn't really matter whether you use Celsius or Fahrenheit or Kelvin. That's well above the melting point of any metal this thing could be made of.
I'm in danger!
So, looking at those numbers, why don't you get third-degree burns from holding sparklers? And why wasn't I burned to ashes in a university basement 20 years ago? Because heat isn't temperature, and it's all about energy. It is a basic human experience that things can be hot or cold. I don't have to explain to you what that means, and everybody has felt it before, sometimes very severely. As to how this can be explained in terms of physics, that's a harder question. Historically, it took a rather long time and a lot of wrong turns until we got to a good description of heat. In the past, people believed it was a substance that could flow between bodies, and it took until the 19th century to figure out what it really was: motion. A lot of people did great work on this topic called thermodynamics, but in the end I chose Rudolf Clausius for the thumbnail because he had the best pose and the best stare. Anyway, motion. Motion of molecules, to be precise, the smallest components of a body. So obviously we had to develop a concept of atoms and molecules to make further progress. Molecules can move or rotate or jiggle, all of which is a form of motion, but an undirected, random one. So while the molecules do move, they do so in many different directions, so in total the body itself does not move. Well, not much anyway. And we will return to this point in future when we will discuss Brownian motion and thermal expansion. We call the energy which is in the random unordered motion of the molecules thermal energy. When two bodies with different thermal energy are in contact with each other, the faster moving molecules will bounce into the slower moving molecules, transferring a part of their energy. And that's why heat can only flow from a hot object to a cold one. It's a transfer of motion. Temperature is a measure for the average kinetic energy of a single molecule. And that's why there is an absolute zero point of temperature, namely when the molecules stop moving completely. This happens at about minus 273 degrees Celsius, and it is the definition of 0 Kelvin. This also answers the question why very high temperatures do not necessarily have drastic consequences, like the sparkler example or the plasma from the intro. High temperature only means that the individual particles have a high energy. But if you're getting only a small number of those particles, like a single spark from a sparkler, that is not a lot of energy in total. And it's all about the total amount of energy transferred, so heat. If you increase the number of particles in a plasma, for example, it will absolutely melt any containment therein. And that's one of the big problems of building fusion reactors, actually. I hope these examples make it very clear that the difference between temperature and heat is not just some words in a book that you have to learn in school. It's a difference between this and this. And this concludes our public service announcement that heat isn't temperature. Leave a like and subscribe, and don't touch open flames. And don't do plasma in your basement. Thank you.